Today we're working on section 4.3, which is on real zeros of polynomials, and we want to start out talking about the rational zero theorem. So again, we're given a polynomial, p of x, and we see it there. This is again just the standard form for any polynomial, and so it has integer coefficients. Then what we know is every rational zero of p will have the form p divided by q, and if you remember, rational simply means that it's a fraction, and so the fraction is going to be p divided by q. Now, where do we get these numbers? P has to be a factor of the constant term, a sub 0, the last term that you see. Q has to be a factor of a sub n, which is the leading coefficient. So we are going to examine those two numbers to help us find out the possible rational zeros of this polynomial function. So the first thing we want to do, find the possible rational zeros of this. So we look at the constant term first of all, because again, the top number in our fraction comes from the constant term. So we have 8. So we want to think, what are the factors of 8? They're the numbers that are going to be on the top. Then for the bottom number, we have 3, because 3 is the leading coefficient, and so on the bottom we're going to have factors of 3. So for the top numbers, you could have a 1 plus or minus, a plus or minus 2, plus or minus 4, or plus or minus 8. On the bottom, we just have options of 1 and 3. So then we have to put together all the combinations of those. So we can have plus or minus 1 over 1, plus or minus 2 over 1, plus or minus 4 over 1, plus or minus 8 over 1. Then we can have plus or minus 1 over 3, plus or minus 2 over 3, plus or minus 4 over 3, and plus or minus 8 over 3. And those are going to be all the possible rational zeros that we've got. So for example 2, we want to find the rational zeros of this polynomial function. So first of all, we want to write down the possibilities. And remember, the possibilities are the top number will be factors of 2. The bottom number will be factors of the leading coefficient, which is 1x cubed. So the only possibilities we have here are plus or minus 1 over 1 and plus or minus 2 over 1. So as we look at these, we're going to check these using synthetic division, like we have learned before. And so we're going to try, I'll just try 1. We have 4 different options we could try. So we've got 1, 0 for the x squared, negative 3 for the x, and 2 for the constant. So remember, we bring down the first term, which is a 1. That's going to be a 1. Add those two together, we get 1. Multiply 1 times 1, we get 1 again. That's a negative 2. Negative 2 times the 1 again gives us negative 2, and that works out. So what we have is that 1 is one of the rational zeros for this polynomial function. So now remember what we have left. This is now x squared plus x minus 2. And if we want, we can just factor this, or at least we can try. So notice we've got x and x. This tells us the signs are different, so one's positive, one's negative. And we need factors of 2 that will add up to be a positive 1. So the factors that actually work here are these two. So then, that's equal to 0. That's how we find the zeros. We just set each factor equal to 0. And notice we get x equals negative 2 and x equals 1. So 1 is actually a solution twice, here, and then negative 2 is a solution as well. So there are 3 rational zeros, negative 2 and positive 1 twice. Notice all of those rational zeros are in our group of possible rational zeros. So now this one, It's worded a little bit differently, but again, we're doing the same type of thing. We want to factor the polynomial completely. So as we look at this, we've got the possible rational zeros that we want to try, because I don't know how to factor this with 4 terms. It doesn't factor by grouping. So if we look at this, we've got factors of 6 on the top, factors of 2 on the bottom. So that's plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6, 1 and 2 on the bottom. So let me list out the possibilities. Plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6, then plus or minus 1 over 2, plus or minus 2 over 2 is equal to 1, and we already have that, so I don't have to list that again. Plus or minus 3 over 2, and plus or minus 6 over 2 is 3. We've already got that, so I don't have to list that again. So what we need to do now is, using this, we've got 2, 1, negative 13, and 6. And we need to try and figure out what we can do here. And I honestly don't know what's going to work, so I'm just going to try 2. So let's say we've got a 2 here, and we bring down a 2. That's going to make 4. 1 and 4 is 5. 5 times 2 is 10. That is going to be a negative 3. 2 times negative 3 is a negative 6. So that actually worked out. So now we have 2 as a 0, which means x minus 2 is going to be a factor. So that's one of our factors right there. Then let's see what else might work here. I think, looking at this, I think going from here, I think negative 1 will work. Let's find out. So we've got a 2. 2 times negative 1 is negative 2. That gives you a 3, negative 3. Okay, that did not work, so negative 1 is out. So let me just go back and erase that. And how about a negative 2? Let's try negative 2. So negative 2 will give us, we got a 2 and negative 4, which is a 1, and that'll be a negative 2 again, which is negative 5. So again, that does not work. And let's go with negative 3. Oops. Negative 3. We'll try that. So negative 3, bring this down, you get a 2. 2 times that is negative 6. That gives you negative 1. Times that is a positive 3, and that is a 0. So that will work. Since negative 3 is a solution, x plus 3 is the factor that goes with that. So now, notice we had x cubed when we began. After we found one solution, it was down to x squared, and now this is just x. So this is really 2x minus 1. That's the factor that's left. The ones we divided out were the x plus 3 and the x minus 2. So our function p of x is 2x minus 1 times x plus 3 times x minus 2. So now finding these rational zeros. The first thing we want to do is list the possible rational zeros using the rational zero theorem, just like we've done here in these last couple of examples. Then we want to use synthetic division to check the possible zeros until we get one that has a remainder of 0, which means it divides in evenly. Then we want to repeat steps 1 and 2 using this quotient, or this answer, just like I did on the last example. So let's take a look. Find the zeros, and then we're actually going to sketch this. It's going to be a rough sketch, because we're just going to find the zeros first. But notice the possibilities, plus or minus. It's going to be factors of 10 over factors of 1. So plus or minus 1, plus or minus 2, plus or minus 5, plus or minus 10. Now I'll just give you a little hint here. Very seldom is it ever going to be this last one. And even the last 2 don't happen very often. So we're going to stick with the 1s and 2s a lot of times here. So let's just check 1 here. So our coefficients are 1, -5, -5, 23, and 10. And I don't think 1 is going to work, but let's check it. And 1 does not work. So let's get rid of that. And let's try maybe a 2. So again, we bring this down. 2, that'll be a 4. -1 gives you -2 and -7. That will give us -14, which is a 9, and that'll be 18. So that doesn't work either. Well, and then of course, after I just said that those bigger numbers don't work, let's try the 5. Maybe the 5 is going to be a solution for us. So we've got a 1, gives you a 5 and a 0. 0, -5, -25, -2, -10, and 0. So of course that one worked. Now, the interesting thing is here, we've found a 0, x equals 5. Now what's left is a new polynomial, but notice the constant is now only -2. So now that we've gotten rid of that 5 that worked, we know that these don't work at all anymore because it has to be a factor of 2 now, which is just 1 and 2. The other thing, we've already checked 1, so we know that one doesn't work. So we've only got, and let's say we already checked 2, so we know that one doesn't work. So the only possibilities we have left are -1 and -2. So let's check one of those. Let's check -1. So we bring down the 1, -1, 1, -4, and that one does not work. So -1 doesn't work. So let's go with -2. So we have this so far. This is going to give us 4, -1, 2, 0, and that works. So -2 is also going to be a 0 for us. Now notice what we have left. This thing right here, that's a quadratic. So we can think of this as A, B, and C. And so we can use the quadratic formula once we're down to a quadratic. So this will be 2 plus or minus -2 squared minus 4 times A times C over 2 times A. And that's 2 plus or minus 4 plus 4. So square root of 8. And that's a 2. And again, we can simplify this. 2 plus or minus square root of 4 and square root of 2. So 2 over 2 plus or minus 2 square root of 2 over 2. And so we find out that these zeros are 1 plus or minus the square root of 2, which are some numbers relatively close to 0. So now, as we sketch, remember the things that we have learned. We know we have a 0 at 5. 1, 2, 3, 4, 5. We know we have a 0 at -2. 1, 2. And we know actually 1 plus the square root of 2 is going to be a little bit more than 2. 1 minus the square root of 2 is going to be a little bit negative. So we've got those 4 zeros to look at. Now we want to consider our end behavior. The end behavior, if you remember, it's an even degree and a positive leading coefficient, which means from these zeros, both of these things to the right and to the left are going to be going up. And I'm not going to take tons of time to do a sketch. We're going to do more with sketching later. But what's going to happen is this will come down, go back through there, and back up. And actually, this is stretched out a lot further. It actually probably comes down way further on the bottoms and way up higher on the top. But that's going to be just a quick sketch. There are the zeros that we found. And if you have the graph, you can see it is stretched out a lot, but the idea is there. Our zeros at -2, just a little bit less than 0, a little bit more than 2, and at 5. And then, of course, we had going up to the left and up to the right. Another help that we have for finding zeros is what is called Descartes' rule of signs. And so what this rule says is that we've got a polynomial that has real coefficients. Here's how we find our zeros, or the possible zeros. The number of positive real zeros of p will either be equal to the number of variations in the sign of p of x, or it'll be less than that by an even whole number. So you can write that down, but we'll do some examples to kind of show what that means. But again, what we're considering here is we're looking at variations in the sign in p of x, which means we're dealing with the coefficients. Of p of x. And we want to know how many times do those coefficients change signs. The second part of the rule is that the number of negative real zeros of p of x will be equal to the number of variations in sign, again of the coefficients, for p of negative x, or less than that by an even whole number. So here is an example. Use Descartes' rule of signs to determine the possible number of positives and negative real zeros. So the first thing we're going to do for the positives, and I'll just make a little chart here, positives and negatives. For the positives, we look at the coefficients of p of x. We've got a 3, which is positive. We've got a 4, which is positive. We've got another 3, which is positive. We've got a negative 1, so that's negative, and then a negative 3. And the only thing we care about is how many times does it switch. So this is positive, positive, positive. Now it switches. Whoops. Now it switches to a negative. So that's one change, and then it stays negative again. So it only changes signs one time, and that means there is one positive zero. There has to be. Now, we talked about it can go down by an even number, but in this case, if you've got 1, you can't go down by an even number because that would be negative. You can't have a negative number of zeros. So now with the negatives, we have to actually check p of negative x, which means we replace all the x's with negative x's. So it'll be negative x to the 6th, plus 4 times negative x to the 5th, plus 3 times negative x cubed, minus negative x, minus 3. And then we have to simplify. Now this has 6 negatives, so that's going to still be positive 3x with 6. This one has 5 negatives. That's going to make this negative 4x to the 5th. This one has 3 negatives, so you're going to have negative 3x cubed. This one has 2 negatives. That's going to make it plus x. And then the constant just has a negative on it still. So let's look at our coefficients again. 3 is positive. Negative 4 is negative. Negative 3 is negative. This is now a 1, that's positive, and a negative 3. So we look at how many times this changes. Well, it starts out as positive. It changes to a negative, so that's 1. Stays negative. Changes back to a positive, so that's 2. Changes back to a negative, that's 3. We're not counting how many positive or negatives. We're counting how many times those coefficients change signs. So there could be 3 negative answers. Or remember, we always have the option of going down by an even number, so there could actually also be just 1. 3 minus 2, there could be 1 negative answer as well. So the options are you could have 1 positive and 3 negatives, or since we know there has to be 1 positive, there could also be 1 positive and 1 negative. And so that's how we use Descartes' rule of signs to tell us how many positive or negative answers we could have. Another thing to help us be efficient in our guessing and checking method with the synthetic division is the lower and upper bound theorem. So once again, we have a polynomial p and it has real coefficients. If we divide p of x by x minus b, which means b is positive, using synthetic division, and if the row that contains the quotient, so in other words that bottom row underneath the line, and the remainder has no negative entry, then b is what we call an upper bound for the real zeros. What that means is nothing larger than b will divide evenly into p of x. So we won't try anything that's bigger than b. If we divide by x minus a and a is less than 0, so a is negative, using synthetic division, and the row that contains the quotient and the remainder has entries that are alternately positive and negative, or non-positive, non-negative, then a is a lower bound, so you would not check anything that's less than a. Again, we're going to take a minute to do an example like this, so let's look at that now. We're going to show that all the real zeros of this polynomial, p of x, lie between -3 and 2. So the first thing we're going to do with our synthetic division is we're going to try 2. And notice we've got a 1, 0 for x cubed, -3 for x squared, 2, and -5. So we do our synthetic division. We bring down the 1, and you get a 2, and then a 4, and then a 2 again, and then an 8, and a 3. Notice we divided by a positive, and every one of these answers in each of these entries is a positive. That means no solutions will be greater than 2. So it is an upper bound. Then we're going to do the same thing with -3. We've got 1, 0, -3, 2, -5. Bring down the 1. You get a -3. That gives you a 9. -18 gives you -16. And 43. Now notice this time we were using a negative to divide, and these alternate. Plus, minus, plus, minus, plus. When that's the case, that means no solutions will be less than this -3. So -3 is what we call a lower bound. So if nothing is greater than 2 as far as the solutions, and no solutions are less than -3, then everything, all the solutions, all the real zeros have to be between -3 and +2. So now we want to use these things that we've learned in example 7 to help us factor this polynomial completely. Notice it's 5th degree, and we've got a lot of terms there, so let's start working. The possibilities are going to be plus or minus 1/1, and we're looking at the 9 and the 2 here, plus or minus 3/1, and plus or minus 9/1, then plus or minus 1/2, plus or minus 3/2, and plus or minus 9/2. So once again, I like to start with numbers that are relatively small. I'm going to start with the 1. We've got 2, 5, -8, -14, 6, and 9. Bring down the 2. Oh, before we even do that, we should probably think about how many answers of each type that we can have. How many positives and how many negatives. So for the positives, we just look. This is positive, positive, negative. Okay, that's one switch. Negative again. Back to positive, so that's 2 switches, and positive again. So there could be 2 real positive zeros, or there could be none. We can always go down by an even number. For the negatives, we're going to hopefully try and think about this. When we put in a p of -x, you're going to have 5 negatives here. So that's going to be a -2x squared, x to the 5th. You're going to have 4 negatives here, so that's going to be positive. Here, you're going to have 3 negatives and then 1 more, so that's going to be a positive. Here, 2 negatives plus 1 more, that's 3, so you're going to be a negative there. This 6 will be just 1 negative, and then the 9 is going to be positive. Separate that there. So we've got 1 change, 2 changes, and then 3 changes. So 3 or 1 is the number of negative answers that we could have. So let's go ahead and still check this one. We have a 2 and a 7, negative 1, negative 15, negative 9, and 0. Okay, so 1 works out, which means we know it's not that case where there's no positives. We know there's 1 at least, so there has to be a second one. So then we need to try something else. Let's go with, what do we have here? Let's try a 3. See if we can find that other positive. So you get a 2, that would be a 6 and a 13, 39, 38. This is getting too big, I think. Yeah, that's going to be way too big. So 3 is not going to work. As much as I don't want to, let's try 3 halves. See if that'll work for us. So you bring down the 2. 2 times 3 halves is 3. That gives you a 10. 10 times 3 halves is going to be 5, and that gives you a 4. 4 times 3 halves is 6, and that gives you negative 9. And that times 3 halves is not going to work out either. Make sure I did this right. 2, 3, 10. Oh. Something didn't seem right. 10 times 3 halves is going to be 15. Wait, where was I? 15 right here. So that's going to give us 14. 14 times 3 halves is going to be 21. And that gives you a 6. And 6 times 3 halves is actually going to be 9. That's going to work. Okay? So notice what we've got now is we've got 1 and 3 halves have both worked. So we've got our 2 positives. I'm not going to check any more positives because we found them both. So now with what's left, look at what happened here. These things are all divisible by 2. So we can factor out a 2, and what's left would be, because this was x to the 5th, and then x to the 4th, so this is now x cubed. What's left would be 2x cubed plus 5x squared plus 7x plus 3. And since we're factoring completely, we can just keep this 2 over here with the other things that we've already factored. So now notice what we can do with the rational zero test. We've got factors of 3, just 1 and 3. And notice we've already found all the positives, so only the negatives could possibly work. So let's check that out using these numbers, 1, 5, 7, 3. Let's try the negative 1. This would be negative 1 and 4, negative 4 and 3, negative 3 and 0, and that works. So negative 1 is another 0. And now notice we've got it to this point. This is x squared plus 4x plus 3. We're down to a quadratic. Let's just factor that. And we get x plus 1 and x plus 3. So here are 2 of the factors. The factor we get from this, remember, is x plus 1. So that's going to go down here again. Now remember we have this 2 and this. The factor we get from this is x minus 3 halves. Just to make it more convenient, we're going to combine that with the 2, and that gives us 2x minus 3. And then finally, we have the factor from this is x minus 1, and so we're going to put that in here also. And so that is how we completely factor a polynomial. Now, it won't always factor out completely like that. Sometimes we'll have a quadratic left over or some imaginary stuff. But in this case, you just keep using your synthetic division, and even though we started out with a fifth power, by doing this process and keeping in mind the upper and lower bound rules and Descartes' rule of signs, we're able to get through this relatively easily.
For example 8, we're going to solve this equation graphically, and you can see the answer is already there, and we're going to round to the nearest tenth. But the way we do this is, of course, we're going to go to the y equals, and we're going to enter in this equation. Well, the left-hand side and then the right-hand side. So 3x raised to the fourth power plus 4x raised to the third power minus 7x squared minus 2x minus 3. And then probably the easiest way then is just to go down and in the second half, or the second equation, put in the right-hand side, which is just 0. And then we're going to graph, and again to graph and get back to that normal screen, we're going to push zoom. And then we're going to go down to number 6 for zoom standard. And we'll see what we see here. Okay, it looks like this intersects 0 in 2 spots. So the easiest way to do that then is just to go second, trace, down to number 5 for intersect. And then remember, we just have to get over close to the intersection point. Oops, went too far. Okay, so you can see my cursor's there. Here's our intersection point that we're looking at right here. And so then we'll just hit enter for the first curve. It jumps down to the second curve. We hit enter again, and then I don't want to guess, so I just hit enter a third time. And we get one of our answers is negative 2.3 when we round that off. So then we'll do the same thing to find the other intersection. We'll go second, trace, down to intersect, number 5. And again, we'll go to the right now. And again, we just have to get relatively close to that. That's really close to the intersection, but we have to get close to it. Hit enter 3 times, first curve, second curve, and I don't want to guess. And you can see we get 1.3 when we round that off. So those are the two answers we're looking for, negative 2.3 and positive 1.3.
The assignment for this lesson, section 4.3, is on pages 341 and 342, and you can see them listed there. Again, you will have time to work on that in class tomorrow, but please try and get started so that you can ask some questions.